talk is going to be about implementing or enabling sequential consistency on low-RISC SoC. And before I go further, this is a side project that I'm working aside of my day job. So this is not to excuse its immature stage, but it's just a side project. So basically, I'd like to talk about first what sequential consistency is, just to give a brief idea to everyone in the room to come at the same page. And then I'll talk about the low-RISC SoC, which is where we're going to implement the sequential consistency memory model on. And then followed by this, I'll talk about the implementation and the current status. So basically, this is a work in progress talk. The work is not complete yet, but I'd like to talk about its status, future work, and what has been incorporated so far to the processor itself. And the last part will be the remaining work. So to get started, the memory consistency model of a system actually determines in which order the memory writes are propagated to the other cores in the system. So this order, there are basically fundamentally two memory consistency models in which we can classify as sequential and relaxed consistency. Relaxed consistency is sometimes also like closer to weak memory consistency models, in which in sequential consistency, since we're talking about a simultaneous multiprocessing system, every processor issues its memory operations in the given program order. The program order is basically the assembly level of instructions in which must be adhered by the processor. And then, so a sequential order must be maintained for each processor. So the instructions must not be reordered. And then the second constraint is basically these changes in one processor must be propagated to the other processors in the system in an atomic manner. So one processor should not get the changes before the other ones. Whereas in relaxed consistency is a bit of a generic term, but in general, processors can reorder the instructions. Of course, this must be detailed in the instructions set architecture of the processor. And then synchronization is required by the compiler and the program writer itself. So the synchronization points should be there explicitly by the programmer writer. So a bit more detail on the sequential consistency. So as I said, there are basically two constraints. One is the program order, in which a processor shouldn't basically reorder the memory instructions or give that impression or illusion. And the second is atomicity, where basically a write to a memory or cache block should be propagated to the rest of the system in an atomic manner. So during the rest of this talk, there are two things. Basically, first is we talk about SMP system, so all cores are identical. And the second thing is the sequential consistency I'm talking about is about the microarchitecture itself. But compiler also has some directives to give directions to the processor so that it enforces sequential consistency or any consistency model. So basically, we're talking about microarchitectural changes. And just a small, simple example to detail what sequential consistency requires. So basically, these two flags are first initialized to false, and then each processor checks if the other core's flag is true or false, and if it's false, it's going. It's some sort of implementation of a mutex, but not exactly, just a simple form. So under sequential consistency, first of all, each processor executes its operations in the program order. So basically, these processors shouldn't reorder these instructions. So that's why you see the operations are the same. So first store and then the load, and there as well, store followed by a load. So basically, let's assume the first processor goes in and then does the write. So what happens is when processor 1 sets the flag 1 to true, the controller in the processor 1 or in core 1 sends an invalidation message to the processor 2. And then processor 2 now knows that some other processor in the system actually modified the shared variable. So basically, that block goes into invalid state. And then this makes sure that the processor, the second processor actually reads the updated value that has been written by the processor 1. And this invalidation message makes sure that the all processors in the system see the updated value of the flag 1. This, by atomicity, I mean this operation must be done atomically so that all processors see the message at the same time. So if you take a look, this ordering, for instance, is actually a violation of sequential consistency, because if you take a look, P1 or P2 reads a value of false, and then both processors go ahead and update the values. So basically, instructions are reordered. The program order is not regarded, is not adhered. And then if you look at the second case, it's again a violation of sequential consistency, but this time it's because of the invalidations are not done in an atomic way. So that actually, even though both processors update the values, those changes are not propagated to the other processor. So this is just to explain what the term is. And except in 4 factorial cases, there are actually 4 factorial 24 cases in which we can run these instructions between 2 processors. And the only invalid cases are the cases where both processors read false. So I think enough with the sequential consistency. And just as an example of what relaxed consistency requires is basic. Oh, OK. This must be some code snippet, but isn't really visible. Basically, Linux or most of the compilers or OSs provide some primitives so that you enforce certain ordering in the processors. And SMP write memory barrier is one of them, for instance, in which you can find all these instances in the Linux kernel. But OS and compilers basically give those options so that you explicitly do the ordering. So the thing is, there is not a single relaxed memory consistency model. There are lots of models, and different microarchitectures implement different MCMs. For instance, PowerPC does only reorders loads after loads and that sort of things. x86 has total store order, for instance, which you may have heard of. But what we're interested in is, what does actually RISC-V ISA say about memory consistency? So basically, RISC-V ISA employs a relaxed memory model, and it is documented in the ISA. So what it does is, actually, it takes care of the program order, so it doesn't reorder instructions so that so you don't see reordered operations in a single core. But this is good for sequential consistency because that's what it necessitates. But the second relaxed, actually what makes RISC-V ISA relaxed is store operations are not visible to the other processors except the fence instruction is used, unless a fence instruction is used. So basically, this is what the memory model looks like. And as an extension to the base ISA, there's a atomic operations extension in which you can actually have sequentially consistent execution. So, but a recent study actually revealed the violations of this contract between ISA and the programmer. So basically, there's been some, I think this group is from Princeton, and they've run some tests. Since the ISA is known and the memory consistency model is known, they run some tests and check if actually the trace is giving what the programmer expects. But apparently, there were some violations, but violations of RISC-V memory consistency model, what I just described previously. And as I said, this study is focused on memory consistency model of RISC-V, not sequential consistency. So we don't really know if those are violated or not. So I mean, our motivation on working on this work is basically RISC-V ISA, first of all, doesn't provide or give a sequentially consistent MCM. So even though RISC-V ASA specifies a relaxed memory consistency model, this doesn't mean some implementations can actually implement sequential consistency MCM. So that's one of the reasons. I mean, we just want to see if what are the challenges to implement those. And the second thing is we use Rocket cores, and the Rocket chip generator, which is an in-order processor. So it is known that there are a lot of techniques to implement sequential consistency on out of processors, in which those processors have reorder buffers and scoreboard mechanisms, which again takes a little bit effort to implement this, but there are lots of techniques to do this in out of order processors. But in our work, we basically implement in-order processor version of sequential consistency, which makes this work a bit more interesting than the others, because we could have easily gone for an out-of-order model, and actually it still can be done. But then it requires incorporating out-of-order elements to the in-order processor. So before I go to implementation, let me talk about what actually the Rocket chip generator looks like. This you might have seen before, and this SMP architecture is derived from the Rocket chip generator, in which you see every tile comprises of a Rocket core, instruction, and data caches. And then it is an in-order processor with 5 pipeline stages, but we will see that actually the memory system is not actually in order. And the on-chip network is basically tile-link, or tile-link conformant, in which tile-link is a protocol. So it's not a physical implementation, but rather a protocol itself. So the main interest, my main interest was actually the memory system or memory hierarchy of the processor, so which is basically a pipeline cache. And then we have 4 stages in which we get requests from CPU and the memory system, and then reflect those changes accordingly. But what makes, or what is interesting here for sequential consistency is basically the MSHR, which stands for actually missed status handling registers. So basically, RISC-V employs a non-blocking data cache, which means when a write miss happens, normally an in-order or sequentially consistent processor must actually stall the pipeline and wait until the data arrives from, or data is written back to memory, since it was a write miss. But then in case of this non-blocking cache architecture, the cache actually relays the request to the MSHR subsystem, and then just continues issuing the next instructions. So when the instruction completes, the MSHR issues a replay message to the processor itself, and then basically the changes are reflected on the pipeline. And the number of MSHRs are basically configurable during before synthesis, and basically in default configuration there are 2. And the steps on a cache miss on L1 data cache is basically the request is sent, and then once the missing line is fetched, it is replayed by the pipeline. So that's why I said the memory subsystem of the Rocket is not actually in order, because it employs some sort of a scoreboard mechanism to replay the instructions, replay the memory operations once they're complete. And the last part about Rocket chip, before I go into implementation details, is the interconnect, in which this is actually what tiling looks like. So basically, it's a protocol, not the physical implementation itself. And Rocket chip generator uses a tiling compliant interconnect. Basically, there are clients and managers, where L1 cache being one of the clients, and L2 directory might be the manager. There are 5 types of messages: acquire, grant, finish. So we actually added some message for adding sequential consistency as well. And one another important aspect is the default coherency model is this famous messy model, in which a cache line has any one of these 4 states. So, I mean, now that we know the architecture, so the question becomes how do we make this sequentially consistent, and what are the pieces we need to add? So basically, the straightforward method is we can just stall the pipeline until every preceding load and store is committed, which means we get the acknowledgement for it from the memory subsystem or from the L2 cache so that we can continue the next instruction. But then whenever a cache miss happens, the preceding instruction, this induces long latencies in case of cache misses. And then, as I said, the later memory operations are not issued, even though they can be issued. And the second thing is we must ensure that the coherency protocol makes these propagations atomically. And one observation is, I mean, the later memory operations do not really need to wait if they operate on a different memory block. This is for one processor. But then on the other hand, we must make sure that the other processors in the system are not working on the same cache line either. This is one of the key observations. And as I said, the completions must be propagated atomically. So for that purpose, I started implementing this algorithm that is presented on this paper, this atomic SC for simple in-order processors, which basically proposed an algorithm for in-order processors without using any of the out-of-order processor features. So if you take a look, it is efficient and baseline sequential consistency model in which we stall in every load and write or read miss. This, as you see, is the baseline sequential consistency in which the store operation basically stalls the pipeline, and then the load operation cannot go further. Whereas the observation is we can just give this operation to the MSHR, make sure that that operation is being rolled up, but we can actually keep continuing doing the next operation because it is independent of the previous instruction. So this is really a simple example in which the time save is not that much because in this case, as you see, this is a load hit and this is a write miss. But the gain increases if actually we have a load miss here as well, because basically you pipeline memory operations in that case. So what happens is on every cache miss, we obtain a mutex to the memory block or the cache line in which we made a request into. So mutex acquisition basically happens before initiating request. And then the only place where pipeline is stalled is during the mutex acquisition. So if we cannot acquire it, we just stall the pipeline. And then once the miss acquires the mutex, the pipeline resumes and keeps issuing the next memory instructions. So basically, we do not stall the pipeline immediately once we acquire it, but we continue issuing the next instruction. But the key observation here is the next operation also needs to acquire a mutex because it might be modifying or reading a value from another processor which is currently under modification. So we cannot just go blindly issue the later instructions without acquiring mutex. This is the case where we have actually a pending write miss. And then when the pending miss completes or the outstanding miss completes, it actually releases the mutex. And then all other mutexes acquired under its miss shadow. So miss shadow basically means the mutex acquired by that write and any other following read or write operation that happened after it. So this release actually wakes up other processors in which waiting on those mutexes so that they can keep issuing their memory operations. This example is from the paper itself. So basically, the instructions as store A, load B, and store B, load A. And then as you can see, first store A acquires a mutex, and then load B acquires a mutex as well because store A was a cache miss. And then as you can see, even though the store B could have continued on the second processor, it cannot because it cannot acquire the mutex to that memory block. So that processor 1 actually stalls. And then whenever store A completes, it just releases mutexes for store A and load B so that the second processor can continue. This is basically what the operations look like. So, I mean, these are the steps that probably I probably won't go into details on all of them, but it just, on a write miss, we try to acquire mutex in which we share a request to the shared mutex pool. Because as you may have seen, there must be a shared consistent state between all processors so we can coordinate. And if the mutex is available, we just acquire it and handle the write miss. So this can also be a read miss, by the way. It's not only for write misses. And then the shared mutex pool is basically can reside on L2 cache or any other shared directory on the processor. And then the last thing we need to do is we increment basically some sort of write miss counter on every processor so we know there's an outstanding write miss. And then this is, as I said, this is the only place where we stall. If the mutex is unavailable, then we stall the pipeline until the holder of the mutex releases it. And what we do on a cache hit is basically, if this counter is 0, we know that there are no outstanding misses, so we can just continue. But if it's not 0 but greater than 0, then we should acquire the mutex. And if not, if we cannot acquire it, we just stall the pipeline. So this figure you probably remember from one of the first few slides. But I just highlighted the additions in blue components in which are added for enabling this sequentially consistent MCM. So basically, we have this counter called in-flight write miss counter. And this is basically one of like a simple counter, nothing more. It just has enable bits and increment and decrement, nothing more. And then we have this per core mutex bit vector to keep track of what memory blocks we have acquired mutexes into and what blocks are available. And this, as we will see later on, must be kept coherent with the global mutex bit vector directory. And then lastly, we have this mutex controller bit in which we send and receive interconnect messages from the core itself. So there are basically three messages in which we added as tile link messages to the system. One being mutex acquire for acquiring a mutex, and the second one is mutex release. And the last one is mutex probe, in which the request is coming from L2 cache to check if mutex is acquired or not. So all these are incorporated to the every tile that I've just seen in the first slide. And these are, as I said, these are per processor components. And if you look at the global or shared components, we have this mutex vector for basically, as far as I know, in the default Rocket chip generator, there is only one L2 cache and one directory. So there aren't multiple. But basically, for every L2 cache, we can just interleave the mutex bit vector. But I mean, this is a bit misleading because we have only one mutex vector that is shared among all processors. And then as we have this release status table to avoid certain deadlocks in which the cores try to acquire mutexes to the same memory block. So this probably needs some detailed explanation, but I think it is explained better in the paper. Okay. So as for the status, what has been done, we have implemented the per core status, and I have integrated the coherency messages at tiring transactions. So basically, whenever we access some memory block, we just send other cores saying, I have acquired or I have released the mutex for this block. And then I have performed some simple waveform tests. And then the remaining work is actually keeping the global mutex bit vector coherent, because if it's interleaved, things get a bit more complicated than having one global bit vector. Release status table is not implemented yet, so that's another thing, because even in my simple test, I've seen some cases where there happens deadlock between two requests from two different processors. So even though this seems like a simple component, it just makes sure that there are no deadlocks in the system. And then we need to run some validations by running complex assembly programs. So far, I have used simple programs to test the changes I have done so far. And then I think the main test plan is basically generating traces and then checking if they're sequentially consistent or not. For that, we have a tool that has been published and that is planned to be used. And then this is how I plan to test the system. So there are some stretch goals, but as I said, the paper describes 2 methods. We only implement one of them. The second one, if time permits, can be done too. So this basically concludes the talk. And I'd like to thank Alex, Robert, and Wei, who just supported this project from the beginning, and on my questions and on implementation details and on every other aspect. And thank you. This is it.